Now let us see what NP complete problem means and what the factors a problem needs to satisfy to qualify it as an NP complete problem. Right, we will see those, and we will see one theorem in today's lecture. Right, so here we will say that L is in NP complete if the following statements are true about L. Right, so if L is in NP, that means L should be in NP. That means it can be solved in polynomial amount of time using a non-deterministic Turing machine. Now for every language L dashed in NP, there is a polynomial time reduction of L dash to L. That means if there are some complement language, means if L is my original language and its complement, if that complement part we can reduce to L, that means again we are mapping one class of problem to those class that can be solved in polynomial amount of time, right? So if these two works fine, then we can say it is NP complete, right? And there will be certain problems where this any of the two properties may fail, so that will not cover under NP complete problems. That means we are not able to reduce those problems so that it can be completed in polynomial amount of time, right? And if we can successfully reduce the problem with the help of other problem and the total thing can be completed in polynomial amount of time, then we will mark those as NP complete and rest will be classified as NP hard. We will see it. Okay, now an example of NP complete problem is traveling salesman problem. Why? Because you can see there if you remember that using a single tip Turing machine we able to implement this traveling salesman problem in order of n to the power 4, and using multi-tip Turing machine it was order of n square. That is, both the cases are a polynomial term. But if we have not gone through this approach, it was somewhat like order of m factorial, so it was means nearer to 2 to the power cm, right? So it was exponential, but using Turing machine we have seen that using non-deterministic Turing machine rather we can complete this traveling salesman problem in polynomial amount of time, right? Now since it appears that P is not equivalent to NP, means always the problems that can be solved in polynomial amount of time using deterministic Turing machine, and there will be some problems which we cannot solve in polynomial amount of time using deterministic Turing machine, but if we go for a non-deterministic approach, that can be done in polynomial amount of time. So these two are not equivalent always, right? Now all the NP complete problems are in NP minus P. That means there are some class of problems which can be solved in polynomial amount of time using deterministic Turing machine, and there are some, and that too can be solved in polynomial amount of time using non-deterministic Turing machine only as well, right? But if we discard those problems which can be solved using deterministic Turing machine in polynomial amount of time, the rest are what? Only those problems where a non-deterministic Turing machine is must to complete it in polynomial amount of time, and those class will be NP complete problems. Okay, fine. So once we have some NP complete problems, we can prove a new problem to be NP incomplete by reducing some known NP complete problem to it using a polynomial time reduction. We have already seen the approach using which we can do this thing. So if we have a previously known NP complete problem as say traveling salesman problem, so if a new problem is given, if we can reduce that problem according to traveling salesman problem, and we have already know the approach that okay, using non-deterministic Turing machine this traveling salesman problem can be solved in polynomial amount of time, so we can follow that path only. But beforehand we have to go for a construction algorithm we have seen, and that construction algorithm should be should be able to execute in polynomial amount of time. That much we have to do, right? Now the following theorem shows why such a reduction proves the target problem to be NP complete. Okay, we will see that. Now what the theorem is saying here, if P1 is NP complete and P2 is in NP and there is a polynomial time reduction of P1 to P2, then P2 is NP complete. So you will say, okay, we know this fact. If P1 is already proven to be NP complete and P2 is again NP, then if we can reduce my there is a reduction algorithm of P1 to P2, that means if we can map my P2 with P1, then P1 is known to be NP complete, so we can prove that P2 is NP complete as well. But we will just see the formal proof, that if we have to do it formally, how it would be like. We need to show that every language L is in NP polynomial time reduces to P2, right? Now we know that there is a polynomial time reduction of L to P1 and this reduction takes some polynomial time Pn. Fine. Thus a string W in L of length n is converted to a string x in P1 of length at most Pn. Now if we have a string that is W in L, okay, in means language L, that is of length n, and that can be converted to a string x in P1 of length at most it will be Pn, right? And we also know that there is a polynomial time reduction of P1 to P2, and we are assuming that this reduction is also consuming q of m amount of time. Okay, now if this is so, then this reduction transforms x to some string y in P2. That the reduction is we know that reduction can be done in this fashion. If we can reduce some x to some string y in P2, that means we are reducing the strings of my P1 to some strings of some P2. So it will take what? If you just see the previous slide, there we have seen that this x value was at most consuming p of n time, and my y, that is in P2, it was q of m. So here m will be what? That is p of n. That means the total time will be at most q of p of n. And thus the transformation of w to y takes at most what? Total its original time, that is Pn, plus the newly generated time, that is q of p of n, so which is a polynomial. So we can conclude that L is polynomial time reducible to P2, right? And that's why we can directly claim that if P1 is NP complete and P2 is NP, and if a reduction algorithm exists, then P2 will also be NP complete. Fine. Now there is one more important theorem to be proven about NP complete problems. If any one of them is in P, then all of NP is in P, right? But here since we already know this, we will just see one line proof here. You can take some problems and can try it of your own. Now suppose P is both in NP complete and in P, right? Means P is such a problem which can be done or which can be executed in polynomial amount of time using a non-deterministic Turing machine, and it can be done in polynomial amount of time using a deterministic Turing machine. So what is the better approach? Means, so we can say that it can be done in polynomial amount of time using a deterministic Turing machine. If it can be done in polynomial amount of time using a deterministic Turing machine, definitely it is going to be done in polynomial amount of time using non-deterministic Turing machine. That's why if this kind of situation occurs, so these are the class of problems where my P will be equivalent to NP, right? So this was theorem 2. Now there are again some problems which we call NP hard problems. What are such problems? Some problems L are so hard that although we can prove condition 2 of the definition of NP completeness, that is every language in NP reduces to L in polynomial time, we cannot prove the condition 1. That is, we cannot prove means there is no way out to solve any problem using a non-deterministic Turing machine as well in polynomial amount of time. It is going to consume exponential amount of time in whatever way you approach, and or more than that, right? So it cannot be completed, or it cannot be mapped using non-deterministic Turing machine even, right? So this for this kind of problem we called it as intractable, and intractable means are those problems which are NP hard, right? Those cannot be reduced to NP complete as well, or it cannot be implemented using in polynomial amount of time using any non-deterministic Turing machine. Fine. So fine. So the factor could be even like p equals to np, right? So there may be some problems again if you can even prove this one, and still L will take exponential amount of time. So again, means at the end of the day you cannot come up with any approach where you can reduce this problem in to get executed in polynomial amount of time. Okay. Now let us see what the satisfiability problem says. Why we are moving to the satisfiability problem here? Because in next class we are going to prove a theorem called Cook's theorem. There we need this for proving our NP completeness. Okay, we will see that in our next class. Here the Boolean expressions are built from what? The variables whose values are in Boolean, that is either they have value true, that is 1, or false. We know this, all this thing. And there are some binary operators, namely the logical AND is denoted with this sign, and logical OR is denoted with the second sign. There are unary operator, and this is called logical negation. We're just recapitulating all this because we know all this thing. Now if we have to go for precedence, the parenthesis to group together, and we know the precedence will be like this is unary operator is having the highest precedence among the operators, and then and then OR, right? Now if we have to see this one, if we are having an example of x and not of y or z, right? The sub expression y or z is true whenever either variable y or variable z has the value true. We know that. Or works in which fashion? If either of the value is true, then the output will be true, right? And if both of them are false, the output will be false. Now if we put a negation sign just beforehand, it will just work in the reverse manner. That is, it will be true when exactly both y and z are false, and it will be false in all the other three choices, right? Now finally, if we have to consider the total expression, it would be like what? Since it's a logical AND of the two sub expression, it is true exactly when both the result of not of y or z is true and x is true, right? When both of these sub expressions are giving as a true result, then my total result is true, otherwise it will be false. Okay. Now see, a truth assignment for a given Boolean expression E assigns either true or false to each of the variables mentioned in E. Now the value of expression E given a truth assignment T, we denote that ET. Truth assignment means, do not think that truth assignment means true. Truth may be either true or false. Okay, that is we are depicting it as E of T. Now is the result of evaluating E with variable x replaced by the T of x, that is true or false, and T assigns to x. We know this, means how we evaluate Boolean expression, we know this, but just for recapitulating purpose we have to know what is the satisfiability problem is. That's why we are just recapitulating all. Now a truth assignment T satisfies Boolean expression E if ET is equals to 1, that is truth assignment T makes expression E true. So this will, we will say that what for which assignments to which values, means for which value of x, which value of y, and which value of z, my output is total true. So that truth assignments will be considered as my means for these values my problem is getting satisfied, right? So Boolean expression E is said to be satisfiable if there exists at least one truth assignment T that satisfies E. That means for any one assignment out of all the choices, you know that for 3 variables there can be how many number of assignments? Total 8 number of assignments, right? 2 to the power 3. So for out of 8, if at least any of the output is true, we will say that that Boolean expression is satisfiable. For other, we will say no, it is not satisfiable. Now you can see if we reconsider this example which we were talking so far. So if we assigned x equals to 1 and y equals to 0 and z equals to 0, for this particular value it is coming to 1. So this is one of the assignment for which my total value is true, so it is satisfying for this assignment. Okay, now we will see one more example where whatever value you assign, it will never satisfy, right? So you can see here again, you can try it of your own. Just let us pick up the middle factor, that is not x or y. So it can you put any value for which it is going to give us a value, true value. Say we are just assigning x equal to 0 and y equals to 1, right? So okay, so for this one it will give a value 1, right? Fine. So let us see if any choices are possible, right? Now you can see here, now there are we have seen an example where an expression has exactly one satisfying assignment and an example where it has none. Okay, so you can just see here that if we just assign these values for this expression, right, say not x or y, so if we just put this one x equals to 1 and y equals to 1, so it is going to return 1, right? If we put x equals to 1, y equals to 0, 1, again same. But if we just put x equals to 0 and y equals to 1, it was going to satisfy. Fine. But if you see the whole expression which we have seen in the previous slide, if we visit the previous slide again, the total expression is like x and negation of x or y, and then and with negation of y. So just put all the values of the two variables, so there will be 4 combinations, and see whenever this middle value is going to give us 1. So for all the choices, there are 3 choices for which the middle value is going to give us a value with 1, but at the same time the x and y will have some values either 0 or 1, and if we evaluate the total expression for all the 4 combinations, you can see that you will never be able to come up with one resultant as a whole. So this problem is unsatisfiable. Okay, so the first example what we have seen is satisfiable, and the second example what we have seen is not satisfiable. Okay, now if we have to say what a Boolean what a satisfiability problem is, so it is nothing but we will be given with a Boolean expression and we will be asked, okay, is this satisfiable problem or not? If you can come up with any combination for which the output is 1, at least one combination should be there, then my Boolean expression is satisfiable, otherwise it is unsatisfiable. Okay, and from now we will use this concept of SAT, or we will use the satisfiability problem as SAT. Okay, now let us see how to represent the SAT instances. Okay, the symbols in the Boolean expressions are and, or, and negation, the left and the right parenthesis, and the symbols representing the variables. Okay, these are the total symbols that can represent, because there can be zeros and ones only, and there can be left parenthesis, there can be right parenthesis, or this and, or, and negation operator can be there. Okay, the satisfiability of an expression does not depend on the names of the variable, only on whether two occurrences of variables are the same variable or different variable. So here just we have gone to the details of the SAT instances representation. Here say we are given with some variables x1 x2 like this. So if we are representing those variables by x1 x2 x3 or x y z, the meaning is same, so we can replace it. Okay, since sometimes if we have to use a suffix, it is difficult to represent, so if we can just use only the variable name, it is sufficient enough. So we can just convert it according to our need. Okay. So since there are infinite number of symbols that could in principle appear in a Boolean expression, we have to have a familiar problem of having to devise a code with a fixed finite alphabet to represent expression with arbitrarily large number of variables. So then only then we can talk of SAT as a problem, that is a language over a fixed alphabet consisting of codes for those Boolean expression that is satisfiable. Okay, so what we will do, say we are having infinite number of combinations. For each expression there can be infinite number of combinations. So if we have to implement all, so there may be a problem. So from the total set of problems, this is the beauty of satisfiability, we will just pick up those combinations for which the expression is satisfying, right? Because for rest of the cases it is just false, so there is no meaning of taking it off, right? So we will just take off those combinations for which it is satisfying. Okay, to code it, right? So the code is going to use these things. It will just use the symbols as it is, and the variable xi is represented by the symbol x followed by zeros and ones that represent I in binary, right? So here you can see one variable, if it is xi, so x will be there, the variable, and whatever the value of I is, that will convert, say I is equals to 2, so we will convert 2 into binary and will write accordingly. Okay, thus the alphabet of SAT problem has only 8 symbols. All instances of SAT are strings in the fixed and finite alphabet, so there will be total 8 symbols. You can consider what are those, that is and, or, negation, open parenthesis, closed parenthesis, and this x and the 0 1, right, representation of the suffix. Now let us see if we have to code it off. You can see here what we are doing. Just remember for which value means it was holding correct, fine. For now we will just code it off. See here what we are doing, we are just replacing x with x1, y with x2, and z with x3, because if we do not do like this, we cannot represent the suffix with binary values. Okay, so if it is like this, then my total expression will be x1 and negation of x2 or x3. So here 1 means if we represent it in binary form, it will be 1. If we represent 2 in binary form, it will be 1 0, and if we represent 3 in binary form, it will be 1 1. So it will be looking like this. Okay, now the length of a coded Boolean expression is approximately the same as the number of positions in the expression, counting each variable occurrence as 1, right? The reason for the difference is that if the expression has m positions, we can have order of m variables, right? So if this the number of variables, so there can be this much of positions present, right? And so the variables may take order of log m symbols to code. Why log m? Because we are following binary pattern. Okay, so there will be 2 choices, so that can be converted to order of log m. This total m variables can be coded in order of log m time, right? So if we have to do it for m number of positions, each is taking order of log m, so that will be turn out to be a order of m log m. So if we have to code any expression in binary format or any Boolean format, that is not binary, it's a Boolean, because we are also using in the operators as well, that is and or negation. So if we have to represent it boolean in boolean expression, the time consumption can be maximum of order of m log m. Fine. So this much of today, and you can see why we have learned this. In next class you will see we will cover this Cook's theorem, and that in there we will pick up this SAT problem, satisfiability problem, and we will come to a conclusion using that theorem. This much for today. Thank you.